Okay, in section 3.4, we're going to look at how to actually determine the rate law based on results of experiments. Okay, so let's take a look at a specific example because it's the best way to learn it. So here we have nitric acid reacting with chlorine according to the equation that's given. We have run experiments where they have changed concentrations of their two reactants. And it says the following initial rates of reaction have been measured for the given reagent concentration. Reagent is another word for reactant. And what I'm given is the rate in molarity per hour for both NO, varying amounts of NO to start and varying amounts of chlorine to start. So let's take a look at how we go about solving this. So we know that the rate is going to be some rate constant K times the concentration of NO raised to some exponent we'll call X times the concentration of chlorine raised to some exponent called Y. And what we're trying to do is figure out X and Y. Okay, so let's take a look at how we would do that. If I want to look at what's happening as I adjust the concentration of NO, I want to find an experiment where I'm keeping chlorine constant and perhaps doubling NO. So if I look at that, I can do that using experiment 2 and experiment 1. And if I do that, and if I look at the ratio of my concentrations, I have, in experiment 2, I have 0.5, in experiment 1, I have 0.25 molar. If I divide those, I get 2. If I use the same experiment now, experiment 2 over experiment 1 for the rate, I get 4.79 over 1.19, which gives me 4. So what I have to look at is 2 to what power is going to give me 4. And in this case, X is going to be 2. So NO is going to be to the second power. Okay. We're going to do the same thing now, finding the order with respect to chlorine by looking at keeping NO constant. So to do that, if we look, we can see experiment 3 versus experiment 4. The concentration of Cl2 is 3 over 1.5, which is 2. If I compare the rates, divide experiment 3's rate by experiment 4 rate, I get 2. So now I say 2 to what power gives me 2, and that is going to be 1. So Y is 1. So chlorine is first order. So the overall rate is going to be the concentration of NO2 times the concentration of chlorine. And if I go back, I need a K here, right? So let's say we're asked to solve for K. Let's figure out what we would do there. So what I can do is I can take any one of these 3 experiments and plug into the value to my rate expression and calculate the rate. So let's pick experiment 1. So if I rearrange the equation, K is going to be equal to rate over the concentration of nitrogen times the concentration of chlorine. So that's 1.19 molar per hour over concentration of NO squared times the concentration of chlorine squared. And when I do that, I get a number of 12.69. But let's look at what happened to our units. Again, I'll remind you that I said units are really important in this unit, and you can do a whole bunch of great work, and if you don't have your units right, you might lose all of your point that's associated with that FRQ. Alright, so let's take a look at just our unit. So if I have meters over hours, and then when I squared 0.25 molar, that becomes molar squared, and 1.5 molar just gives me molar. So if I change the molar per hour, I'm going to put the hour in the denominator. And then I also end up with molar squared and molar in the denominator. So the 2 molars will cancel, and I'm left with 1 over hours times molar squared. So my final units are going to be hours to the minus 1, molar to the minus 2. Okay, so let's move forward and look at another problem. Here we have a hydroxide ion is involved but not consumed in the reaction. So here we have our reaction, and over the arrow we see OH minus. That's a way to indicate that OH is a catalyst. It's not consumed in the reaction, but it does affect the rate of the reaction. So anything that we have that's not an actual reactant that gets consumed, we put it over the arrow. Okay, from the data in the table, determine the order of reaction with respect to the 3 reactants. And then we need to write the rate law and determine the value of K. Alright, so let's clean up a piece of paper a little bit, make it easier to see. Alright, so if I look at this, the rate is going to be equal to K times the concentration of the OCl times the concentration of the I times the concentration of the hydroxyl raised to the X, Y, and Z respectively. Alright, so I got to find the order, I've got to find X, Y, and Z. So let's do OCl first, and in order to do that I'm going to keep I and OH constant. And if I see I've got, from experiment 1 to 3, I have a ratio of doubling of the reactant, and if I look at the rates for the same experiment, they also give me a value of 2. So my X there, I double the reactant, and that leads to doubling of the rate. That's going to be first order. X is going to be equal to 1. If I look at I, where I keep OCl in OH minus constant, I can look at experiment 2 and 3. And when I do that, the ratio of my concentrations is still 2, and the ratio of my rates is also about 2. Now these are not perfect values, and that's because these are experimental data. And we, as you know, we don't get perfect experimental data out of the lab, and you'll see that when we do kinetics experiments. This is also about 2, so Y is going to be 1 also. Right, the last thing we're going to look at is the hydroxyl concentration, and if we evaluate experiment 3 and 4, what I see is a halving of the reactant concentration, and if I look at the rate data, that's doubling. Okay, so I got to ask myself, 1/2 or 0.5 raised to what power is going to give me 2? And I'm using Z here, so Z in this case, this is a reciprocal of 1/2. 2 is a reciprocal of 1/2, so Z must be -1. Okay, so my rate expression is, if I put in all the X, Y, and Z, I get K times concentration of OCl times concentration of I times the concentration of OH minus to the -1. Okay. Now it also asked me to find the order and what is the rate law. Okay. So go ahead and try this and make a choice. Okay, welcome back. So if I look at experiment 1, I can look at any experiment. That's what I do, right? I look at any of the 3 experiments, or I guess in this case there's 5 experiments, and I just put in the values in the table, and I solve for K. So if I rearrange the equation, K is going to be the rate over the concentration of the reactants raised to the order. So I'm going to use experiment 1. I'm going to plug in the information for each of these values, and when I do that, this is what I'm going to get. If I plug it into my calculator, I get 30. But let's take a look at the units. So on the numerator, I have meter per second, so I'm going to go ahead and make that meters over seconds. I have meters squared in the denominator here when I multiply, I'm sorry, not meters, molar times molar. And this 2m to the -1, it's a reciprocal, right? So I put that m on the numerator. And when I do that, I end up with meter squared canceling out, so I end up with 1 over seconds, or s to the -1. So my answer is going to be 3.